This video is going to hopefully make exponential growth a little bit clearer for you. I'm going to do an example with you and explain what's going on, because I know when you get to problem 4 on worksheet 85, you're like, what is going on? So let's look at this kind of real life situation. Let's say Helen Woodward's animal shelter saved a puppy that was born on July 1st, weighing only 2 pounds. He grew to 150 pounds at 1 year old, or 12 months. That's important because our time we need to keep consistent. So when we're doing stuff in months, we have to keep it in months. I can't put in a 1. I have to put in a 12 when I keep things consistent. If the puppy gains weight proportional to its own weight, then how much did the puppy weigh on New Year's Day? Well, here is the sentence you have to look at. If the puppy gains weight proportional to its own weight. Well, what does that mean? Well, the puppy's gaining, so that's a change in his weight. So he's there's a change in his weight, so over time, and it's proportional, some value k of his weight. So a puppy gains weight. The change in weight over time equals some proportional value to its own weight. And that's how we set up the problem. And then we're going to go through the same steps that we did with the other problems like this. We're going to do separate variables. Separate variables. Take the integral of both sides. Okay, so let's first get all the w's on this side. So we get dw over w equals k dt. Now when I take the integral of both sides, we're going to get ln w equals kt plus c. Okay, then that's going to set us up for finding out what c is. We're going to use the initial condition to find c. Well, in this problem, c, when he was born, okay, at time 0, he was 2 pounds. So we're going to plug in ln 2 for weight equals, I don't know what the scale factor was or the proportion was, but I do know that at time 0 he was 2 pounds. So if I plug that in, I get c equals ln 2. Now that's going to set us up so we can fill in right here ln w equals kt plus ln 2. Now that sets up our equation and gets us closer to figuring that out. What I need to do now is use additional info to find what my proportion was, or my k factor. So what's something else I know? Well, I know that at 12 months, this little puppy grew into be 150 pounds, right? I still don't know what the proportion factor is, but I do know this information. So we're going to plug this in to solve for k. So at ln, his weight was 150. Still don't know k, but I know that happened at 12 months, plus ln 2. Now we're going to start solving for k. Solve for k. And here we get, to get rid of the natural logs, we're going to take e to both sides, and we're going to get 150 equals k, or e to the k12 times e to the ln 2, because remember, plus, I can change, when I have this e to the something and there's a plus, I can change it to multiply, and then this cancels out, and I can now simplify this to 150. This is just a 2, but I'm going to move it to the front. 2e to the k12. So now we're going to divide by 2. 75 equals e to the k12. Now it's kind of funny because I applied e to get rid of the ln. Now I want to apply the natural log to get rid of the e, because I'm trying to get this k by itself. So I'm going to take ln of this side and ln of this side, and we're going to get ln of 75 equals k12. Now I can see that if I divide both sides by 12, I get k equals some crazy number. So we're going to go to our calculator, and we're going to plug in, can you see that? we're going to plug in ln 75. You can't really see that. ln of 75 divided by 12, and it gives me 0.359791. So I'm going to go back here, and I get k equals what was it? 3599791. I could round it, but I'm going to try to keep it as many decimals as possible to be more accurate. And what am I going to do with this? Well, now I know that my scale factor, I can go back here and I can plug it in right here. Hold on. My video paused for a second, and I don't know where I left off because I just kept talking. So I'm going to back up a little bit. So we plugged in 150, and we were solving for k. And so 150 was my I had L and W, KT. I applied E and plugged in 150 for the weight, so we ended up getting 150. We talked about that when you have e to the power where there's some things being added together, you can change that to multiply. This e cancels out, and I can take this 2 and move it to the front, and we get 75 e to the k12. And I want to actually solve for e, and what's just kind of funny because we applied e here to get rid of the ln, but now we're going to apply ln to get to the e. So we get ln of 75 divided by 12. We get k equals 0.35971. Well, that is the proportion. The puppy grows at a rate of 0.395 per month. And so what we're going to do is we're going to take that and plug it back into our original equation. Well, our original equation is actually right here. Okay? The weight, whatever the weight is equal to the beginning amount, e to the kt. So this is where I'm talking about the formula BERT, and when you get these crazy problems where it sounds like a scientific lab experiment, you have your beginning amount, initial amount, times e to the rate times time. Well, our problem was we were developing this formula and we had to find out what k was, and we certainly did find it out, and we got 0.359. So now I can write this equation, and this gives me the weight at any time. And so what I'm going to do is I'm going to plug in the weight. I'm going to find the weight when time is 6. And time was 6 because if you look back at the problem, we wanted to know when how much did the puppy weigh on New Year's Day. He was born on July 1st. So we counted out, or I counted out, look at July, August, September, October, November, December, and then January. So that's 6 months. So I'm going to put a 6 month into my equation. So I come back over here, and I just change this t to a 6. And I go to my calculator and I type that in. And what I want to show you is that at 6, I got 17.3205. And if you're like me, you're thinking, well, how did that puppy go from 17 pounds at 6 months old to 150? So I would, like you, was thinking that was crazy. So I took the same formula and I plugged in a 12, and sure enough, look, it turns out to be 150 if his weight continues to grow at that same proportion over the time of his life. So with that being said, I wanted to take a quick look at number 4 on worksheet 85, because that talks about the same thing. Okay, we have to do the same process, but the question's worded, sometimes the words are a little different. I want to make sure you understand how it's set up. So oil is being pumped continually at a rate proportional to the amount of oil left in the well. So we're going to go, oops, drop my calculator. I'm going to dropped it again, 85 number 4, and you can look at 85 while I read it. It says, the oil being pumped in from a certain well at a rate proportionate. So the oil, what are we going to call it? I'll call it Y, okay, because DO sounds weird. Y represents the oil. The oil being pumped in, dy, at a certain rate, and it's always pumped in relationship to time, is proportionate to the oil left in the well. So ky. And y is the amount of oil left in the well. Okay, so initially there were 1 million gallons. So at time equals 0, we know there was 1 million. Okay, 1 million. So the question, and then 6 years later, here's another thing it tells me. 6 years later, there was only 500,000 gallons in the well. And it's no longer profitable to pump when there are fewer than 50 gallons. So that's just a little piece of information for part C. But let's part A, it says write an equation. This is what we just did with that puppy problem. Okay, what was the first thing? Separate the variables. So we get dy over y equals k dt. Then I'm going to take the integral. Separate variables to take the integral. So when I take the integral, we get ln y equals kt. K, remember, is a constant, plus c. So now I'm going to use initial condition. And I know that at time 0, my y equals 1 million. So we're going to get ln 1 million equals k times 0 plus c. So you can see that c equals ln 1 million. Okay? So that means I can now take this formula right here and write ln y equals kt plus ln 1 million. I'm going to use the second piece of information now to figure out what my proportion is. So my second piece of information was t was at 6, so I have k times 6 plus ln 1 million. Nice fun numbers here. And then my y was 500,000. So this is going to be ln 500,000 equals. Right? Let's solve for k. What do we have to do to get k by itself? I'm going to subtract ln of 1 million. So we have ln 500,000 minus ln 1 million equals k6. Well, when it's a minus, you can write that as ln of 500,000 over 1 million. And guess what? I can now reduce that. So I get ln of 1/2 equals k times 6. And the next step is we are going to divide by 6 because we want to solve for k. So divide by 6 and we get that k equals ln 0.5 over 6. Oops. Ln, let me write that as k equals ln 0.5 divided by 6. Okay? All right. Whew, that helps us out. So now we can go write our original equation. Remember, our original equation is right here. So we're going to get, well, actually my original equation, I can write it a little bit better than that, because here I could take e to both sides. En of ln y equals e to the kt plus 1 ln 1 million. Sorry, you probably can't see what I'm writing. And then that changes it to y equals, remember this is e to the kt times e to the 1 ln 1 million. Okay, that cancels out. This 1 million is my constant, so it's y equals 1 million e to the kt. So there's my equation, and now I can plug k in there. So now we're going to get, make this. So now my equation is y equals 1 million e to the k, which we just found out was ln 0.5 over 6, times t.